All right, good morning, Townview. Let's go ahead and start. So today we're going to be talking about the last of our solubility rules. Most of y'all who are in here know what solubility is. Can y'all tell me what solubility is real quick? All right, so the ability to dissolve in a liquid. We were talking about solubility curves, and what we know is that when we increase the temperature of our liquid, what happens to the solubility of a solid? It goes up. So what we're going to be talking about today is whether something will dissolve at all. So what you guys should notice is I just handed you guys the full periodic table, the STAR chemistry reference materials. Downstairs, y'all should have this too. So we started the year by just using the periodic table, then we moved to polyatomic ions, and then semester 2 we used this sheet right here that gave you the gas laws and then all these constants that you need. But moving forward, you're going to need the whole thing. So everyone should have a stapled version of that together. What we're going to start with is we're going to look at this page right here. This is the page on the back of the periodic table. We're going to be looking right here in the middle where it says solubility of common ionic compounds in agua. Y'all see that? So this topic that we're about to get into right now, it's not very heavily tested, so I don't want to get into making y'all memorize any rules. All you need to know about solubility is not everything will dissolve in water. And this list will show you the common things that will not dissolve in water. So here at the top, what we have is the solubility section. So this right here, everything in this list is going to be soluble. And what do you notice about the charge of all of these things? Well, all but one. They're mostly negatively charged with the exception of ammonium right here, which has a positive charge. So when you're looking at whether something is soluble or not, are you looking at the beginning or the end? You should be looking at the end of it. So let's go ahead and solve these right here. See if I can close that. Nope. Just made it worse. All right, so here's what we're going to do. We're going to take a look at our first one. The first one is going to be ammonium acetate. And we can look at the ammonium, we can look at the acetate, but what I like to do is just look at the very end. So acetate is right here. Is acetate soluble, yes or no? It is soluble. Are there any exceptions to the rule? There are no exceptions to the rule, which means anytime you see something bonded with acetate, that thing will be soluble. So on your sheet, the worksheet that I just handed you, we're going to label it yes for solubility. So before we move on, what I want to show you guys is an example of something that will not dissolve in solution. So over here, what we have is lead iodide precipitating. What you see is we have a clear aqueous liquid here at the bottom, and then we have a clear aqueous liquid at the top. When we mix these two, watch what happens. Who wants to see more of that? How pretty is lead? This is lead right here. So lead is extremely toxic. Most of y'all already know that. It's very toxic to children. They used to use lead in paint. I'm gonna pause this and show my students something. All right, so what I wanted y'all to see from this video is we started off with 2 aqueous solutions, and once they mixed, what we were left with was still an aqueous solution with some spectator ions that you can't see. And then the yellow mercury, the yellow lead is a solid. That's what I want y'all to see. So this lead is a solid, and we can remove the solid just by filtering our solution. So let's come back over here. So we decided that this ammonium acetate solution will be soluble in water, which means it's going to dissolve in water. If it dissolves in water, is it going to form an aqueous solution or a solid within the solution? Aqueous? It's going to be aqueous. So anytime it does dissolve in the solution, it forms an aqueous solution. Now let's look at the next one. The next one is barium hydroxide. So we're going to look for hydroxide. Here's hydroxide right here. So hydroxide is on the insoluble list, which means if we put some hydroxide in water, what's going to happen? It's going to form a solid in solution, but it's got exceptions. So the exceptions to it are if it's bound to ammonium, if it's bound to an alkali metal cation. So what's an alkali metal? All right, so group 1. Not group 2. This only applies to group 1. So when we say an alkali metal cation. So hydroxide's exceptions are NH4, alkali metals, calcium, strontium, and barium, which are all group 2 elements. Yeah. So that's it. These are the exceptions. Now looking at this one here, it's bound to barium. So does that meet one of our exceptions? Yes, it does. This one right here. So is barium hydroxide soluble? Yes, it is. So even though it's on the insoluble list, because we meet one of the exceptions, it does become soluble. So if you put it in water, does it form a solid or an aqueous solution? It's going to be aqueous. Next one we have is iron carbonate. Here's carbonate right here. And our carbonate's bound to an iron. Our exceptions for carbonate are going to be NH4 and alkali metals. Is iron an alkali metal? No, it's not. So is it soluble? No, it's not. So what's it going to form when we put it in the solution? It's going to form a solid. Good. Let's get the next one. We have sodium hydroxide. So back to hydroxide right here. Does sodium meet any of the exceptions on this list? Yes, it is. It's an alkali metal. So is it soluble? Yes. Is it going to be aqueous or solid? It's aqueous in solution. Next one, rubidium nitrate. So here's nitrate right here. Is it soluble? Are there any exceptions to the rule? No. So solubility, yes or no? Yes. Solid or aqueous? Aqueous. All right, easy, right? So this lesson, we're only going to spend about less than 10 more minutes on it. I'm going to give you guys, we're going to do 8 minutes to finish up this worksheet. I only want you to do the front. And you saw how easy this was. So don't work with a partner. I want you to do this on your own. If you don't know how to do it, feel free to ask your neighbor. But I want you to try these on your own because you're not going to see these until we get to the ACP. You won't see them again. So go ahead, work through this. I'm going to pause my recording. All right, so you should have been given somewhere around 10 minutes to finish up the rest of the worksheet. Once you're finished with it, you're only going to submit a photo of the front side. The front side is 1 through 25. We'll see if we can make time for the back page sometime next week. So one more thing that I'd like to discuss before we move on to our next topic is the other type of question that you're going to see. So most likely what you're going to see on the test is they're going to give you 4 examples. So they'll give you 1 through 4, and those are going to be answer choices A, B, C, and D. And they're going to ask you which of these is insoluble in water, and you're going to need to be able to label all these. So yes, no, or whatever. You just got to label all of them, and then you choose the one that's that meets with what they're asking for. So this is one type of question that you're going to see. Now the other type of question that you're going to see is going to look more like this. So they'll give you a total of 4 equations, and they'll ask you which of these forms a precipitate. Now what I showed you, what you learned on this last worksheet is, so which is the precipitate? Is it the aqueous solution or the solid? So if it's the solid, what should you be looking for in terms of solubility? You want something that's insoluble, right? So over on this page, let's take a look at it. If you are looking at all of these, and I'm going to label these A, B, C, and D, which of these does not form a precipitate? Are you sure? All right, the correct answer is D. Why does D not form a precipitate? Or how do we know that it doesn't form a precipitate? It doesn't have a solid. So it's a crucial part of understanding this section right here. Precipitates are always going to be solid. So this last one here, this is a neutralization reaction. So we have an acid, we have a base, you put them together, you form water, and then usually you form a salt. In this case, we have an aqueous salt, but we don't have any solid in solution. So because we don't have a solid, this would be the one without a precipitate. All 3 of these have a precipitate, and it's the solid. Any questions? All right, so that's it. Everyone should have turned that in. Let's go ahead and move on to the next thing. So next up, we got molarity, and this is posted for you guys in Classroom. So go ahead and open that up. I suggest you having this open as we go through it. You don't need to write the answers that I'm putting in down. There are some notes that I want you to take from this, some definitions that I want y'all to know. So molarity, how can the concentration of a solution be expressed quantitatively? Could somebody tell me what quantitatively means? All right, so numerically. Can somebody give me an example of something that's not quantitative? Yes. Say it again. Sure. What's another one? A simpler one. Well, when we say quantitative, we're talking about numerical. So think of something that includes numbers, and then think of something that doesn't include numbers. But I see what you mean by hair color. Hold up. Do y'all want a funny joke? All right, this one's one of my favorites. If y'all don't laugh, y'all don't get it.
Oh, that's good.
Y'all get it?
Yes.
But anyway, beauty is not quantitative. You can't put a number on it. I know some of y'all be talking to your friends like, oh, I just met this person on a scale of 1 to 10. Where they at? You know what I'm talking about? You can't quantitatively judge people, or you shouldn't at the very least. But when we're talking about concentrations of solutions, you want to be quantitative. You want to know. You want to be quantitative. You want to have numbers. So let's go ahead and take a look at the why. Could somebody read the why for us, please? And let's be respectful. I want to be able to hear what they're saying.
When you buy a bottle of a certain brand of lemonade, you expect it to taste just as sweet as the last time you bought that kind of lemonade. Likewise, when doctors prescribe a certain ointment, they expect the concentration of medicine to be consistent. How do companies ensure their products taste or perform the same every time you purchase them? Many companies, including pharmaceutical companies, keep track of the concentration of a solution by measuring its molarity, a ratio of number of solute particles to the volume of solution. In this activity, we'll learn about molarity and how to represent concentration quantitatively.
All right, let's keep going. All right, so here we have 2 lemonade solutions, and these lemonade solutions are made of 2 components. So we have one, the water. So what is the water, solute or solvent? This is going to be our solvent. Remember, water is universal solvent. And then we have the lemonade mix. I'm just going to dot this. So the lemonade mix, what's that going to be? The solute. So over here we have 2 of them. And you can see that this one's just a little bit lighter than this one. What does that tell us about their concentration?
The second one is more concentrated.
All right, so what she's saying is this one is more concentrated. So there are 2 definitions I want y'all to have. I don't want to give y'all actual definitions. What I want to give y'all is just a spectrum. So over on this side of the line, we're going to put concentrated. And on this side, we're going to put dilute. So concentrated doesn't really tell you much. It just tells you that it's more than, so the middle, if it's concentrated, that means it's going to be over on this side somewhere. If it's diluted, it's going to be more on this side somewhere. But that's basically all you get from those 2 words, which is why we have molarity that actually gives us a quantifiable place. So it'll tell us whether it's here, whether it's here, whatever. But so dilute, concentrate, I want you to have this on your paper. And then over on the concentrated side, we want to put that this side has more solute. It could also have less solvent, but we're just going to put more solute over here. On this side, we're going to put more solvent. Or less solute, however you want to think about it. But concentrated means that it's going to be this darker one. And then diluted is going to be more this one right here. So we're not going to answer all these questions. We're going to skip a bunch of them. Let's go through this one right here. Could somebody who hasn't read yet go ahead and read A for us, please? I'll call on you guys. I'm not scared.
No.
You're not answering these. I just want to go over them with you. Somebody read 2A for us, please. All right, so looking up here, do they have the same or different volumes? Are you sure? They have the same volume. That's something we want to know. And just know, you don't have to write this. I just want to go over this stuff before we talk about molarity. Somebody read B for us, please.
Lemonade solution 1 has more or less the same quantity of solute as solution 2. Describe how you know in terms of number of particles.
All right, so we're comparing 1 to 2 here, and they want to know which one has more solute. So they both have the same amount of solvent, but which one has the more solute? Solution 2. So solution 1 has less solute, right? So for this one, we're going to put less. Now let's move to number 3. So number 3, somebody read this for us, please.
Lemonade solution 2 is considered to be concentrated, and lemonade solution 1 is considered to be dilute. Examine the two pictures in model 1. There's two ways to differentiate a concentrated solution from a dilute solution.
All right, so we're going to come back up here. We already labeled them, so this is our concentrated one. This is our diluted one. And basically what you're seeing here is an example of ppm. Anybody know what that is? Parts per million. So particles per measurement, whatever. Parts per million. So this one is going to have 3 parts per million, whereas this one has 10 parts per million. That's just one way of measuring concentration. That's not how we're going to do it today, though. Let's go ahead and move on. So could somebody read 4A for us, please? Yeah.
A glass is filled with the concentrated lemonade solution from model 1. Is the solution in the glass the same concentration as the solution in the pitcher?
All right, so let's take a look over here. So here we have our glass, and then here we have our pitcher. Do they taste the same, or do they taste different? All right, this cup and then this pitcher. Do they taste the same or different?
Same.
They're going to taste the same. Why do they taste the same?
They're the same concentration.
They have the same concentration. So if we were to zoom into this one, it's going to have the same particles per million as this one over here. So that's what we wanted to see from there. Let's take a look at the next one. Who wants to read B for us?
Does the solution in the glass contain the same number of solute particles as the solution in the pitcher? If no, explain how your answer to part A can be true. Hint, consider both amount of solute and amount of solvent.
All right, so over here, I'm going to erase this stuff. So over here, let's say that we put in 1 cup of the lemonade mix. I'm just going to put lemonade mix, 1 cup of lemonade mix. So does this have 1 cup of lemonade mix?
No.
No, it doesn't. What do they have that is the same, though?
The ratio between the mix and the water.
All right, good. So it's the ratio between the amount of water and the amount of lemonade mix. So that ratio is the same. Their parts per million is going to be the same. Their concentration is going to be the same. We're almost finished. Now we're going to get into actual measurements. So here we have some solutions, but let's move on to down here. We're going to skip 6. That's a waste. What does the letter M stand for in Model 2? So here's the letter M. I want everybody to write this down exactly how you see it. So capital M stands for molarity. In college, you're going to hear about molality. And lucky for you guys, we don't do molality in here because they're confusing thinking about two different types of concentrations. You only have one concentration type to deal with. So capital M stands for molarity. Now, when we read it, let's say we have a 4M solution. That's read as 4 molar. 4 molar, like the tooth. All right, let's move on. So use the data in Model 2 to answer the questions below. Calculate the ratio of moles of solute to liters of solution for each solution. So now we're going to write the molarity equation. So molarity is equal to moles of solute divided by liters of solution. Everybody needs to write this equation. You're going to be using this for the rest of the day. You're also going to be using it next class period. Moles of solute divided by liters of solution. All right, let's move on. So now we're going to calculate the molarity of these solutions. Let's ignore the fact that the answers are already here. All right, let's just go ahead and solve these. So in this first one, we have 0.06 moles of copper chloride in a 0.06 liter solution. So molarity is going to be equal to 0.06 divided by 0.06. So what is our molarity for this first one? It's going to have a molarity of 1. So this is a 1 molar solution. Over on this side, we have 0.18 moles of copper chloride in a 0.06 liter solution. So our molarity is going to be equal to 0.18 divided by 0.06. And what does this equal? This is a 3 molar solution. Easy, right? So to be more concentrated, does it need to have a larger or lower molarity? All right, so the higher the molarity, the higher the concentration. Do y'all want to keep solving these, or are we good? All right, well, let's go ahead and move on. So the worksheet I posted for y'all in Classroom is super easy, but we're not going to work through those. I want to be able to work through these first. So you're going to be working through these with me, and then you're going to work the other ones by yourself. So let's go ahead and take a look at the first one. I would write these down if I were you. Just extra practice, which is going to be good for you. And some of y'all saw that before we started, I changed most of these to moles. What you're going to notice is that we also bring stoichiometry into this section, which means if the answer is moles, it could easily be converted to grams, or it could easily be converted to particles. We're going to be doing that next class. Today, you're going to be getting the simplest equations. So let's go ahead and take a look at this first one. I'm going to start by writing my equation up here. So molarity is equal to moles over liters. So if 10.7 moles of NH4Cl is dissolved in enough water to make a 800 milliliter solution, what will be the molarity? So here we're solving for molarity, and I'm going to write this equation right here. So A is equal to B over C. So we have 10.7 moles. Where does that go? A, B, or C? That's going to be in B, so 10.7 goes here. And then 800 milliliters, where does that go? Can we plug it in as it is? What do we got to do? How do we do that? So you can divide by 1,000 or place the decimal point and then move it over 3 spaces. So 800 milliliters becomes what? 0.8 liters. So that's it. So plug this into your calculator. What's our molarity here? $13 point what? All right, we're going to round that to 13.4 molar solution of NH4Cl. Are we good? All right, let's move on. So the next one also wants us to calculate the molarity. So capital M is going to be equal to 6.8 moles. Where does that go, top or bottom? So 6.8 divided by enough solution to make a 2.5 liter solution. That's going to go down here. So 2.5 liters. Somebody plug that in and give us an answer. 2.72 molar solution. This is too easy, right? All right, next one. How many moles of calcium chloride are required to prepare a 2 liter 0.7 molar solution? So here they give us the molarity. So where does that go? A, B, or C? That's going to be our A. So 0.7 goes over here. It's going to be equal to 2 liters. Where does that go? 2 liters goes down here. And then we're just going to plug in an X. We just got to solve for X. So how do we solve for X in this equation? So we multiply both sides by 2. The 2 goes away. X is equal to what? 1.4. And what's our unit? Moles of what? All right, good. And then in the next question, it says, in mass, what mass in grams of CaCl2 will be required to prepare the above solution? Basically, we just got to convert to grams here. And to do that, we just got to calculate our molar mass. So calcium has a molar mass of 40, and then chlorine has a molar mass of 35.5. So that's going to be 71. You add these together, and that gives us, what is it, 111? 111. And then we just multiply that by 1.4. Somebody plug that in, please. 155.4 grams of calcium chloride. So most likely on the ACP, they're not going to give you math like this. They're going to give you math like this. That just requires one additional step. And to do that, you just got to remember that to go to grams, you multiply by molar mass. To go to moles, you divide by molar mass. And so on and so forth. All right, let's look at the next one. How many grams of potassium nitrate will be required to prepare an 800 milliliter solution of 1.4 molar KNO3? So 1.4 molar, where does that go? A, B, or C? So 1.4 goes here, and then that's going to be equal to X over, what's this? How do we plug it in? So 0.8, and then how do we solve? Multiply both sides by 0.8. This goes away. Now X is equal to what? 1.2? Or 1.12? Do I got it? Is this right? All right, and then the next thing is we need to plug in our unit. So what did we just solve for here? We just solved for moles. So now we have 1.12 moles of KNO3. And then to convert to grams, we just got to multiply by molar mass. But we're not going to do that today. We're going to do that next time y'all are in here. And we're just speeding through this lesson. We're almost done. Y'all are going to have way too much free time. Calculate the volume of a 1.25 molar solution of HCN made from 31 moles of HCN. So we have a 1.25 molar solution. Where does that go? A is equal to B over C. So that's going to be A, so 1.25, and that's going to equal 31 moles. So 31 moles goes at the top, 31. And then here we're solving for X. So how do we solve this equation? Multiply by what? We're going to multiply both sides by X. Then this goes away. And how do we solve from here? Divide both sides by 1.25. And then somebody plug that in. 24.8, and what's our unit? Liters. So anytime you calculate volume, what you're pulling out is liters. Anytime you calculate moles, you're pulling out moles, and molarity is going to be molar. Calculate the volume of a 3.5 molar solution of H2SO4 made from 49 moles of H2SO4. So we have a 3.5 molar solution, which means that's going to be our molarity. So 3.5 goes here. And then that's going to be equal to 49 over X. So we're going to solve this just like we did the last one. Multiply both sides by X. This goes away. And then divide both sides by 3.5. This goes away. And then what's our answer here? 14 liters. All right, let's go ahead and look at this one. How many sugar molecules are present in a 300 milliliter 2 molar solution? So first thing we're going to do is plug this up. So we got 2 molar on this side. That's going to be equal to x over 300, or not 300, this should be 3.3. And how many molecules? So first thing we need to do is we need to solve for moles. How do we solve for moles? What do we do?
Multiply by 0.2.
So then this goes away. And then what?
So this is 0.2.
All right, so 0.6 moles. Now, the question wants to know molecules. So how do we go from moles to molecules? What do we got to do? Do we need the molar mass? What do we need to do? Avogadro. So in your calculator, make sure to put in parentheses 6.02 times 10 to the power of 23, and then give me an answer.
So it's 3.612 to the 23rd power.
Times 10 to the what?
23rd power.
All right, that's it. And this is going to be molecules of C12H22O11. Any questions? All right, so the worksheet that you guys are about to work on, make sure I see the work. I don't want to see just answers in a box. I want to see the work. I want to see the equation. And this is the easiest math we're gonna do. Next time y'all are in here, I'm gonna expect you guys to multiply by Avogadro. I'm gonna expect you to divide by Avogadro, multiply by molar mass, calculate molar mass. All of these things are gonna be required next time. Today, I just want you to work with the equation. So that's gonna be it. Let me end this real quick, and then here's what y'all are gonna be working on. So go into classroom, go into Molarity worksheet. Here it is right here. Bless you. And that's going to be it. Make sure you turn in both assignments before y'all leave today. And have a nice day.